Alright guys, this is 8.5b rational and real zeros. This isn't really the second part to it. The first video was an introduction to kind of remind you on discriminant and solving using square roots and stuff. So the first part to this is more of a review. So if you remember it, you don't have to watch it. If you get kind of lost through this, then go back and look it over. But otherwise, you should be fine, hopefully. So what we're talking about here are, we're going to be looking for roots or zeros. Remember, that's wherever your function crosses the x-axis. So we can graph a quadratic function to find the roots if it crosses the x-axis. So we have values here and here. Sometimes you'll have one root, if your vertex is here on the x-axis, or you can have none if your parabola is, pointing down over here, or it's up here on the side. One way that we can find these, which we've already done, is by factoring. So you could factor your quadratic function and set each factor equal to 0 to solve for that. We can also use the quadratic function. Remember that your discriminant here will tell you how many roots you have, whether they're real or not. Remember, if you have your quadratic function that doesn't cross the x-axis, you have imaginary roots. Okay, we don't really care about those, at least in terms of this lesson here. We will be looking into those, just not right now. So what we're going to focus on are the rational and real roots that we can find here. Okay, now we're dealing with polynomials. We've already done quadratic functions, so those give you the parabolas, which you're more familiar with. Here we're working with polynomials with higher order degrees. So you're going to have like cubics or something to the 4th, 5th, 6th, 7th degree. So that'll be something that looks like this. Okay, so you'll have some kind of function to some degree, and it'll start, and then it'll cross the thing so many times and then keep on going. So what we're looking for is we're going to try to identify the roots that actually cross the x-axis. You will find imaginary roots over here. We don't care about those. So we're just going to be looking at this here. It is going to take a lot of work in some instances where they're not easily factorable. Okay, so we're going to use what's called the rational root theorem. Now I'm going to show it to you right here, and it's going to be kind of confusing. Okay, so we only want to use this when you can't factor. Remember, you want to be looking for sum and differences of squares, sum and differences of cubes. You want to be factoring using grouping, bottoms up, whatever you can do to factor your polynomial down as much as possible before using this, because it's very time consuming. So you're going to have some polynomial in this form. Don't get confused with all these variables and numbers in here. This just means that you have some polynomial like x to the 6th plus some number, x to the 5th, whatever, and then you might have a constant over here. That's all it means. They're just representing numbers. So what the theorem says is if we take all of the factors of this first coefficient out here, so whatever number that is, let's say that's a 7. Well, let's say 8. If we take all the factors of this number here, 8, and we take all the factors of the constant at the end, then any factor, so remember our factors are like this, times this, all of our roots here, are of the form p over q, and it's plus or minus p over q. And so I'll show you how to do that. Don't get too confused. We're only worried about the leading coefficient and then the constant here at the end. So in our first example here, we have 3x cubed minus 5x squared plus x plus 1. The first thing you want to look for is a GCF. There is none. The next thing you want to do is see if you can factor by grouping. So if we were to split this up, we could pull out an x squared, but it would leave us with 3 and negative 5, which we're not going to get here. So this is not factorable by our normal method. So we're going to use this theorem here. Okay, so we can't factor it, so the first thing we're going to take are the factors of our first coefficient here. So that is our q, okay, and the factors of q are just 1 times 3. Now remember, it's always plus or minus for each one. Okay, our last one over here is 1. Okay, so that is our p, and the factors of 1 are just 1 times 1, so plus or minus 1 there. Now we're going to look to see what the factors are. So then you have to do p over q. Okay, so this is p, this is q. So p over q gives you plus or minus 1 over plus or minus 1. Okay, and it gives you plus or minus 1 over plus or minus 3. So we're going to simplify this where we can, okay? 1 over 1 is just 1, so we get plus or minus 1 here. This isn't going to simplify, so we just get plus or minus 1 over 3. These are all of your possible roots here. Okay, so some of these might be real and some of these might be imaginary. We're not sure. So in order to check, okay, so this is kind of like your step 2 here. In order to check it, we have to use synthetic division for one of these numbers. I always strongly suggest that you just start with the whole numbers, however many you have, and then work on your fractions because those are going to take a little bit longer to solve. So I'm just going to start off with positive 1 here. And then you do your synthetic division. So I'm still working with these numbers up here. I have 3, negative 5, 1, and 1. The 3 comes down. 1 times 3 is 3, negative 2, multiply, combine, negative 1. 1 times negative 1 is negative 1, 0. So what we're looking for is we are looking for a 0 remainder. Okay, if your remainder is not 0, then it is not a real root and you have to try the next one, okay? So now I have x minus 1 over here is going to be my first root, and then this comes down. Okay, so we had x cubed up here. This is going to give me 3x squared minus 2x minus 1. Okay, we still have to see if this can be factored even further. So let's see if we can do it with our table. So if we do 3 times negative 1, that's negative 3. Remember, a times c equal to b. So we have negative 3 here. Sums to negative 2. That's going to factor. That's going to give us negative 3 times positive 1. Negative 3 plus 1 is negative 2. That checks out. So we have x minus 1. I'm going to use bottoms up here. So I have x minus 3 over a. Okay, times x plus 1 over a, and then we simplify, x minus 1, x minus 1, 3 over 3 is 1. Here this doesn't simplify, so the 3 comes up, 3x plus 1. Okay, so this is fully factored, okay, this is factored completely. We're almost done. Okay, once you have factored it completely, then you have to solve each one for x. So x minus 1 is equal to 0, add 1 to each side, x is equal to 1. Okay, x minus 1 is equal to 0, it's the same thing, x is equal to 1, so we have a multiplicity here of 2. And then we have 3x plus 1 is equal to 0, minus 1 on each side, 3x equals negative 1, divide by 3. X is equal to negative 1 over 3. Okay, so I'll do that over here. X is equal to negative 1 over 3. So we have 2 roots here. Okay, I'm going to write them here in roster notation. Our solutions are 1 and negative 1 over 3, where 1 here has a multiplicity of 2. Okay, if you're confused what I'm talking about, go watch the review video because I go over this. So we know that if we have some function, okay, where it's going to cross the x-axis at positive 1 and negative 1/3, okay, so somewhere here. Okay, and then we'll go over n values, but this is going to, look something like this, más o menos. All right, here's the practice problem that I want you to go over for tomorrow. If you feel you can do it, go ahead. I have one more example for you that is a little more difficult, and then I have an additional video for you with more examples on it. Actually, that's all I'm going to do right now. Go ahead and just do this, and then I'll have one more video with example problems on it. All right, let me know if you have any questions. Shoot me a remind or ask me in class tomorrow.